Dear students, the topic of my discussion today is Laplace transform. Laplace transform. Before going into the details of Laplace transform, of Laplace transform, I would like to give in very brief an idea of why Laplace transform is required. Laplace transform or Laplace transformation is basically a branch of study using which we can solve linear differential equation arising in the problem of physics and engineering. Laplace transform actually helps us in converting linear differential equation into an algebraic equation, and thus solving an algebraic type of equation we can solve a linear differential equation with the help of Laplace transform. Now before going into the details of Laplace transform, I would like to give an overview of my course of study here. I have divided the entire topic of Laplace transform in four parts. In part 1, I will be discussing about the existence In part 1, I will be discussing about the existence of Laplace transform, some preliminary ideas of Laplace transform, and some standard formulas which will later be used in developing the subject. In part 2, I will mainly focus on the properties of Laplace transform and some related problems. In part 3, I will focus on inverse Laplace transform and some of its properties and some illustration of the properties. In part 4, I will be taking some more properties of inverse Laplace transform and how they can be applied in solving the entire concept of Laplace transform can be applied in solving linear differential equation. This is how I will proceed. In today's lecture, I will be mainly focusing on part 1. Now, before defining a Laplace transform, let me give a very brief introduction of integral transform, which is a more broader aspect of Laplace transform, we can say. Uh, Integral transform definition. Before defining an integral transformation, let kpt be a function of two variables p and t, where p is a parameter which may be real or complex and is independent of t and is independent of t. then the function if p is equal to minus infinity to plus infinity kpt ft dt. Let us change this function by writing it in caps. Then the function fp equal to minus infinity kpt ft dt is called the integral transform. Is called the integral transform of ft. We must also remember this function kpt is called the kernel of the transformation or integral transformation. Okay, this is all about integral transformation. Now, from here, we will deduce the definition of Laplace transform. Now, we come to the definition of Laplace transform. If the kernel kpt defined in the previous section is defined as kpt is equal to 0 for t less than 0 and e to the power minus pt for t greater than equal to 0. Then if p is equal to 0 to infinity e to the power minus pt if t dt is called the Laplace transform of ft if we name this equation as equation 1 if equation 1 is convergent. is denoted by either Laplace transform of ft or f by p. Now, Laplace transform, we want to note one point here. The transformation here means the Laplace transform exists if integral in equation 1 is convergent, or otherwise it is divergent. Otherwise it does not exist. This is all about the definition of Laplace transform and its existence. Now we will move to an important property of Laplace transform, which we call the property of linearity. Laplace transform actually satisfies the linearity property. So let us now start to see the existence of linear property by the Laplace transform, or rather this how the Laplace transform of a given function satisfies the linearity property. For that we will actually write a theorem. Laplace transform of ft satisfies the linearity property. Satisfies the linearity property. That is, if we can write, that is, let us not write if here. Now, this is the statement of the theorem, and I will give a very simple and straightforward proof of this theorem. To prove this, we know Laplace transform of ft is equal to 0 to infinity e to the power minus pt t dt, which is actually equal to 0 to infinity e to the power minus pt. In place of ft, I will substitute here a1 f1 t plus a2 f2 t dt, which will then become equal to a1 0 to infinity e to the power minus pt f1 t dt plus a2 0 to infinity f2 t dt, which is nothing but a1 Laplace transform of f1 t plus a2 Laplace transform of f2 t. Now, before going into further discussion about the existence of Laplace transform, I would like to discuss and define piecewise or sectionally continuous function. To discuss the piecewise or sectionally continuous function, let ft be a function defined in a closed interval t lies between a and b. If we can subdivide this interval into finite number of subintervals, and in each of these intervals if t is continuous, each of this interval if t is continuous and has finite right and left hand limits, then we say if t is piecewise or sectionally continuous. Now we will discuss about the existence of Laplace transform in form of a theorem. Now, existence of Laplace theorem. This is my theorem 2. If t is a function is piecewise continuous, in the range t greater than equal to 0 and satisfies mod of f t less than equal to m e to the power at, where m is a constant and a, or we can say for t greater than equal to 0 and any constant m and a. If this is the case, we will say that the Laplace transform t exists for t greater than a. We can easily prove this theorem also. Now, Laplace transform of t can be written as e to infinity e to the power minus pt ft dt. Since ft is a piecewise continuous function, we can write it in as 0 to t0 e to the power minus pt ft dt plus t0 to infinity e to the power minus pt ft dt. Now, since ft is a piecewise continuous function, the first integral exists. For the second integral, this can then be further written as after this I am writing here, this can then be written as substitute the limit, then the value 0 to infinity e to the power minus pt ft dt is less than equal to m times this value is from 0 to infinity. So this will be sorry, there is some mistake we are doing here. This is not 0. This value is actually t0. Then this is t0. This is t0. Then this value will be equal to e to the power minus p minus a into t0. Now this can be made as we please. This can be made as small as we please by making t0 large. Hence, from this we can say Laplace transform of ft exists for p greater than a. This is all about the existence of Laplace transform, and I would also like to recap one fact here, that this is a sufficient condition and not a necessary condition. That means there can be problems which satisfies this. If there are problems or functions rather which satisfies this condition, then it is quite obvious that that function Laplace transform will exist. But on the other hand, there are functions which will not satisfy this property, but still then their Laplace transform exists.